Welcome all of you, and we begin our course by this session. So this could be kind of introductory, and we're going to discuss about vectors in general in this session, that contributes to our first module of our syllabus. So let's see what are vectors. We are familiar with this word vector. What does this mean? So we have seen in physics, or in almost all our previous applications, we have seen vectors as a physical quantity which has both magnitude and a direction. Right. So we start with that concept, and in mathematics we have a much more general sense or a general meaning for vectors. So what we plan is we start with the meaning we know as a quantity, a physical quantity having both magnitude and direction, and we move towards the general definition of vectors. In between, we may use several properties of vectors, both algebraic and analytical, and let's see how does it go. So how did we denote vectors? Suppose A is a vector. To distinguish A from a scalar, we had a custom of using an arrow over A, or just a bar over A. That's all fine. Suppose, unlike scalars, vectors had components. Right, vectors always had components. And if A is a vector in 3 dimensions, we used unit vectors I, j and k to denote the vector A as some a1i plus a2j plus a3k. Sometimes we may use I cap, j cap and k cap, where I, j and k are unit vectors in the direction of coordinate axis. Like if we have coordinate axis of 3 dimensions, say x, y and z, then I is the unit vector in the direction of x, j is the unit vector in the direction of y, k is the unit vector in the direction of z, and this is by convention. Okay, so this is how we consider I, j and k. And using I, j and k multiplied with certain scalars a1, a2 and a3, we form the vector A. Right. So this is how a vector looks like. But sometimes in our course, mathematically, we may denote this same vector as A is equal to A1, A2, A3. We may not use I, j and k rigorously, always. But remember that these two notations are the same. Right. So what we have to take care of here is the order of arrangement of A1, A2 and A3. You cannot write this as A2, A1 and A3. This or the order is fixed here. Since if you change the order, that will reflect here and the vector may change. Right. So take care of the order. The vector A, which is A1i plus A2j plus A3k, can also be represented as an ordered triplet with components A1, A2 and A3 in the same order. Right. Now hope you remember the magnitude and direction. Like how do we calculate the magnitude? What do we mean by the magnitude? And all these things, they're fundamentals, and we don't move towards that anymore. And I hope the notations of I, j and k are clear now by this time. So in our analysis, these A1, A2 and A3 will be real numbers, and I, j, k are unit vectors in coordinate directions. Okay. So next fundamental concept we need to discuss is curves. Curves. What are curves? Prior to moving to curves, see, why do we need curves along with vectors? In our further analysis, we may observe these curves as the graph of certain vector functions or vector valued functions. We'll see what are they. So for now, let's see what is a curve. A curve is nothing but a graph of a function in a plane or a space. Suppose we have a plane here. Let this be x-axis, let this be y-axis. And suppose we have a function y equal to f of x. Right. That function obviously will make a graph here. Correct? So such a graph may be called a curve. A curve. Right. And we have a little more excited concept of parametric curves here. I think we should visit parametric curve once we discuss vector valued functions. Right. So what is a vector valued function? And once we define vector valued functions, we will come back to parametric curves. So what is a vector valued function? Vector valued function. You know what is a function, right? Function is a kind of relation which takes something to something. Right. If you say y equal to f of x, the function f carries x to y, or the function maps x to y. Perfect. So similarly, what is a vector valued function? A vector valued function is a function whose values are vectors. See, when we have written y equal to f of x, the function value or the value of the function is y, which is a real number here if you choose both to be real numbers by default. Right. So y equal to f of x has both x and y as real number, and this is a real valued function. We call so since the function value or the value of the function y is a real number. But instead, if we have a vector as the value of function, for example, let f of t or f of x whatever equal to some t square I plus t square I plus 2tj plus t cube k. See, function can happen in this way as well. Here we had a scalar here, a real number here, but the value of the function is not a real number but a vector. As we have seen before, this may also be denoted as f of t equal to t squared 2t t cube. We may not use ijk always. Right. So such a function whose value is a vector is called a vector valued function. A vector valued function. Right. So if you try to plot this in a graph, how do we plot a function or how do we plot a graph? See, we have 3 coordinates here. So obviously we may need at least 4 dimensions to designate this, or 3 dimensions to plot this point, at least a point from this graph. Right. So we just identified this with our normal Cartesian coordinate system x, y and z. Right. We choose the first coordinate to be the x coordinate, the second coordinate to be the y coordinate, and third coordinate to be the z coordinate. And if we have values for x, y and z, we can plot the points and together they will make the graph. Right. Now, as a graphing technique here, we choose the first element to be x. So x is chosen to be t square and y is chosen to be 2t, z is chosen to be t cube in this particular example. Okay, in this particular example. So you can observe that x is now identified as a function of t. See, as t changes, x can also change. Similarly, as t changes, y will change and z will change. So x, y and z are now expressed as functions of t's. So x is no more just x, it's x of t now, y of t and z of t. See, x of t means x is now a function of t and y of t means y is a function of t and z is a function of t. Right. So, actually, if we try to draw a graph or in a space, maybe in a space, in a 3-dimensional space, where we have x, y and z. Actually, what changes here is the x value, y value and z value. But instead of directly changing x, y and z values, we use an intermediate parameter t. Right, remember our former expression f of t equal to some t square. So I just write x of t now. You know that x of t is t square, y of t is z of t. Right. So instead of directly changing x, y and z, we use a parameter t, and as t changes, x changes, y changes and z changes. So t controls x, y and z, and t is called a parameter, and such an equation or these three equations where the parameter is involved and the connection between x, y, z and parameter is expressed are called parametric equations. Parametric equations, and the curve of such a curve, such a function, or the curve drawn by such parametric equations are called parametric curves. Parametric curves. So simply, in layman's sense, parametric curves are the curves of parametric functions or curves determined by parametric curves. So what is a parametric equation? Instead of directly defining in terms of x, y and z, we use a parameter t or whatever, and we explicitly define x, y and z in terms of t. Right. We will see examples and things will be much clearer then. So this is about parametric curves. We have a lot of examples. Consider a function r of t given us. R of t equal to say some a cos t. Let it be a sin t. Right. Or just let it be so. So what does this mean? It has only two coordinates. So it's actually a vector in the two-dimensional plane. Right. This means a cos t I plus a sin t j. Okay. So what figure does this represent? What is the parametric curve, or what is the curve determined by this equation? See, we have seen that we identify x with the first coordinate component a cos t, and we have the second component identified with the second coordinate a sin t. Square them both and add them. What is x square plus y square here? A square cos square t plus a square sin square t. Right. This is x square plus y square equal to a square can be taken outside, and we will have cos square t plus sin square t, and this is cos square t plus sin square t is 1. So we got x square plus y square equal to a square, and this is the equation of a circle. This is the Cartesian equation of a circle centered at origin, having a radius a units. Right. So the graph of this equation, the graph of this vector equation, or the parametric curve determined by this vector valued function is the circle centered at origin with radius a. We will be seeing similar examples in the due course, and we will learn how to convert from this Cartesian equation to parametric equation and so on, and then vice versa from parametric equation to Cartesian equations. Right. So that gives us an example, and we have seen the graph. So now let's see how do we find, or how do we conduct experiments of calculus on vector valued function. And the first concept is about limits. You know what do we mean by limit of a function, right? So what do we mean by limit? Suppose we have a real valued function y equal to f of x, right? What do we mean by limit x tends to x naught f of x equal to L? We have seen this in our previous classes. With this mathematical statement, we mean that as x is allowed to move infinitesimally closer to x naught, but remember, x is never reaching x naught. X is never going to be equal to x naught, but x is moving arbitrarily closer to x naught. f of x has a tendency to move towards L. F of x will move arbitrarily closer to L. Remember, similarly, f of x need not be L, right? But f of x will have a tendency to move towards L. Clear? So this is what we mean by limits for real valued functions, and the same is applicable as a definition for vector valued function. Suppose we have a vector valued function r of t given as, say, f of t, g of t, h of t, which means r of t is a vector function with components f of t, g of t and h of t, or r of t equal to f of t I plus g of t j plus h of t k, where f, g, h are any functions of t, right? Then limit t tends to t naught r of t equal to some x naught, y naught, z naught. See, this may not be a real number then. This may not be a real number then. Means as t goes to t naught, the value of the function as a vector has a tendency to move towards this vector. Okay, we'll see a little more clear ideas in examples. Don't worry about this. What I would like to emphasize is about the trick to find the limit of a vector valued function. The trick to find the limit of a vector valued function comes directly from the definition itself. So remember this expression: limit t tends to t naught r of t, where r of t is f of t, g of t and h of t, is, this can be easily evaluated as limit t tends to t naught f of t, comma, limit t tends to t naught g of t, comma, limit t tends to t naught h of t. So what we do here, to find the limit of a vector valued function, we individually apply limits to each component function. Right, we individually apply limit to each component function, and these are simply real valued functions of t, and we know how to calculate the limits, and we will get whatever, say f naught, g naught and h naught, whatever that may be, that has to be regarded as the limit of this vector valued function. Right, this is how we evaluate the limit of vector valued function, and in our next session we may observe a few examples, and let's move towards continuity.